helping you feel alert and awake and alive. Great. Okay, so I'm going to tell you some more stories about topological defects today and actually talk about experiments a little bit and trying to make models that match actual experiments. So remember all that time we spent looking at the XY model and understanding topological defects in the XY model? Here's a picture of an actual experiment. This is a symmetric freestanding film, so it means a few layers of symmetric where the layers are in the, say, called the XY plane. They're stacked on top of each other, just a few of them, and they've gone through a phase transition from the symmetric A, where the molecules are parallel to the layer normal on average. You lower the temperature, and they spontaneously tilt. If you look from above, the tilt direction represents a vector field, right? And that vector field can have topological defects. If you view that thin film through cross polarizers, you see the defects. Here is a close-up of two defects, one positive and one negative. I can't tell which one is positive and which one is negative unless I rotate the polarizers, and one will turn to the right and one will turn to the left, right? So, and this is our XY simulation. And that's more or less what a symmetric A looks like. So the molecules are not all exactly vertical, but their average orientation is vertical, but they have obviously some fluctuations. And then in the symmetric C phase, they're tilted. Okay, so that's what we've been studying. Now let's consider another class of materials, lipids. Unlike symmetric C, so in the symmetric C, every layer is identical. The molecules may, if they're not end-to-end symmetric, might be oriented in either direction in each layer. Lipids have a hydrophobic and hydrophilic part. So the hydrophilic part is the polar head of the lipid that looks a little bit like a lollipop with a floppy tail, right? And the hydrophilic part and the hydrophobic part make a bilayer. And you guys are probably familiar with lipid bilayers. They're in every cell in your body. They're ubiquitous in biology. Okay, and they also have phases and phase transitions, but in this case, it's not pure lipid I'm looking at, but lipid in water. Okay, so there may be water all over the place. So here is an untilted phase. So the lipid has its head and its tail oriented on average parallel to the layer normal, like the symmetric A. And here's a tilted phase, so that's called L-alpha, sometimes called the liquid crystal phase. And the tilted phase is sometimes called the gel phase. Not all gel phases are tilted, but some gel phases are tilted. It's called the L-beta prime. Okay, so the heads and the tails are organized so that water is excluded from the region where the tails are, and the heads are the part that are in touch with the water. So in particular, if you have a lipid vesicle, like a cell wall is a sphere, you would have the hydrophilic heads facing out towards the water and in towards the water on the interior of the cell, right? With the tails kind of hiding from the water. We were talking about outreach this week. I did an outreach project with kids where I brought a giant bunch of lollipops, and we built lipid bilayers, cross sections on the table with the heads and the tails, and then they got to eat lollipops. What could go wrong with that? We studied my cells. We stuck the tails of the lollipops in a piece of styrofoam. We had so much fun. Anyway, so that's something about lipid phase transitions. The gel phase is a little bit more complicated than a symmetric C because the degrees of freedom in the tail are also freezing out, and so it's a little bit more than just a tilting transition, but the symmetry is the same as the symmetric A to C transition. Okay, so what happens in a flat freestanding symmetric, like that picture I showed you, like the freestanding film, is that when you go through an A to C transition, the net topological charge is typically 0, so you'll nucleate a whole bunch of plus and minus defects, and if you wait for a while, they'll pair-annihilate and pair-annihilate until nothing is left. So here's my question. If we have something like that with a lipid in a vesicle, so now it's in a spherical geometry, what will happen when you go through that same kind of transition from an untilted phase to a tilted phase? Yeah?
What drives the transition?
Temperature. So you're cooling it, so you cool from symmetric A to symmetric C. Likewise, you cool the lipid and it goes through a phase transition. This is not going to happen to the cell walls in your body on a cold day. Do not worry. I mean, unless you freeze to death, right? But it's something that can happen in the laboratory. And I'm not going to study living cells. In this particular case, the vesicles are essentially water balloons made of lipid. So water on the inside, water on the outside, floating in water, Okay, they're neutrally buoyant, same density, the water inside has the same density as the water outside. It's a little lipid sphere, it's a bilayer, okay, and it's going to go through a phase transition. What's going to happen to that thing? Do you have any idea? First of all, we talked about the hairy coconut theorem, the Gauss-Bonnet theorem. There's no way for the tilted phase to be free of defects. So there have to be defects. What's going to happen? Okay, so here's the experiment. Linda Hirst is a physicist at the University of California at Merced. It is the newest University of California campus. It's maybe 90 minutes drive from San Jose. Okay, so this big round balloon-looking thing is what the vesicles look like when they're in the untilted phase. And they can have fluctuations in shape. You can mush them. I mean, they're like balloons, right? They're soft, squishy, round things, but their equilibrium shape is round. Then she cools it into the tilted phase, and that's what it looks like. Okay, it looks all wiggly and crumpled. She did a leakage assay. Sometimes they leak, sometimes they don't. Okay, and if they leak, they look maybe a little bit more crumpled, but they can crumple without leaking. It's not just related to leaking. So the question is, physicists try to do all kinds of things. One of the things I'm trying to do here is figure out, where does this pattern come from? Why is this material changing its shape? Okay, what's happening? Why would something nice and smooth become something all crumpled? Okay, and the question is, could it have something to do with topological defects? Okay, so the Gauss-Bonnet theorem tells us that we have to have a total topological charge of +2. We know there have to be at least 2 defects where the tilt goes in, goes out, or goes around. Remember how we all leaned out of the room and leaned into the room? We have to have 2 of those. But you can have extra plus-minus pairs and still satisfy the Gauss-Bonnet theorem. It's just that the net topological charge has to be +2, but you can add as many extra plus-minus pairs as you want and still satisfy. Okay, so one of the things I showed you, the torus, this was not a floppy thing. This is a solid, rigid torus with an XY model. These are not lipids, these are just XY spins. And what we learned from that is that curvature has an influence on the defects, that the positive defects have a preference for regions of positive Gaussian curvature, and negative defects drive negative Gaussian curvature, are attracted to regions of negative Gaussian curvature. So that same type of coupling between the defects and the curvature can work the other way too. If the surface is flexible and fluid, where there's a positive defect, you might actually have the membrane get more curved. Okay, theorists have been working on this problem. Let's see, so Greg Huber working with, Bob Helkowitz and Tom Powers. I don't know Jan, I'm maybe a student of one of those 3 people. Considered the question of what happens if you have a vesicle in a tilted phase and it has exactly 2 +1 defects. And they calculated, and actually Tom Lubensky and other people have worked on this problem. And they said, well, the region near the defect is going to get more curved. And so instead of being a sphere, it'll get an ellipsoid. It might look like a cucumber. It might look like a watermelon. But it's not going to look like an orange. It's going to be a bit elongated. That seems like it would make sense. So that's the prediction. Okay, so a tilted vesicle with 2 defects, if the +1 defects make the curvature, the Gaussian curvature stronger. If there happened to be a -1 defect, which there is not in this picture, you would think it would make the membrane flatter, right? So if it had Gaussian curvature because it's a sphere, it would get locally flatter, or it might even become saddle-like, because that would have negative Gaussian curvature. Let's compare with experiments. Here's the theory of what a tilted vesicle should look like. Here's the experiment of what the tilted vesicle actually looks like, and they don't agree. They just don't agree. Okay, so our hypothesis is that the disordered shape is related to something about the defects. So if we start with, if you imagine that when everything tilts, when all the lipids tilt, they tilt in random directions. Initially there would be some whole population of plus and minus defects with a net topological charge of +2. And then they would anneal. So if defect motion is fast compared to how fast the membrane actually changes its shape, we could imagine a scenario where many defects nucleate initially, then they anneal until there's only 2 left, and then after a long period of relaxation, the thing would stretch out and become like that. Okay, so this would be the ground state of the system. Okay? But sometimes the system doesn't get to the ground state. If the defect motion is slow, then you can generate a whole bunch of defects, extra plus and minus defects. Everywhere there's a plus defect, the whole thing could pook out and get more curved. Everywhere there's a minus defect, it could get more flat. And then maybe there would be some energy barrier that would prevent the defects from hair annihilating, and you would get some kind of disordered shape. That wasn't our idea, and we wanted to see if we could figure out how that would work. Okay, now the question is, we want to test that idea with the simulation. My first thought was, hey, why don't we just, lipids are molecules, we'll do a molecular simulation. Here's a picture of a molecular simulation. It's from 7 years ago. But even so, that's a lot of degrees of freedom. Now, let's say a vesicle is microns, order of magnitude microns in diameter. How many lipid molecules are there in, say, a sphere of diameter 5 microns or 10 microns? Pick any number you want. And the answer is too many for me to simulate. Okay, so the number of molecules you can actually simulate in a molecular dynamics code, I already told you guys, not very many people here have expertise in computational chemistry. You guys haven't been doing molecular simulations. But even if we're dealing with, say, copper atoms, we can do millions to tens of millions to a billion maybe. That's not even close to enough to do one lipid vesicle. And besides, the lipids themselves have many individual degrees of freedom. It's not just the one atom, right? It's many. Even if you do a coarse-grained model, if you have one coarse-grained particle per molecule, you're never going to get there. You need something even coarser. Okay? And the other issue is shape. When chemists study molecular simulations of lipids with full chemical representation, they typically do a small square patch. And you might be able to watch that patch tilt or untilt, but you don't get any information about the shape of the whole vesicle. Now, there's a whole world of computational chemists who use coarse-grained models for lipids, but they're still thinking about one coarse-grained particle as one molecule, and none of those is going to work for a system of this size. You can study little tiny micelles, but you can't study great big objects filled with water and things like that. So we need to have a model that's at an even coarser grained scale, where one so-called coarse-grained particle doesn't represent one molecule. It represents a whole patch of membrane, which would involve many, many molecules. Okay, so looked in the literature. We found a really nice coarse-grained model developed by a guy named Ju Li. Okay, not Julie, but Ju Li. Li is the last name. Ju is the first name. I believe he's at MIT. He's moved around quite a bit. He was at Penn, now he's at MIT. And his model was reminiscent of a toothpick on a tomato. Okay, so his goal, actually, when he was doing this work, he was a postdoc with Subra Suresh, who went on to be head of NSF, but anyway, at MIT, and they were trying to think of simple ways to model cells. I know many of you are interested in there was one of Christina's students here who's modeling cells, right? They wanted to come up with a simple way to model the cell membrane. And instead of trying to model the whole bilayer and have many, many lipids, they said, let's just have a particle with a vector degree of freedom that represents the preferred layer normal. And when you have two of these particles, they would energetically prefer to assemble like this, and not like that, and not like that, but they would like to be parallel. So if you put these particles randomly in space and they aggregate, they'll make a two-dimensional structure. And his potential, I don't want to bore you with too much of the mathematical details, was designed so that the system would assemble into two-dimensional structure and not crystallize. I'll ask you one more time, has anybody here ever done a simulation with the Leonard-Jones potential, say in 2 dimensions? Nobody at all? Physics, chemistry, they're all the same thing. We all need to fix it up. Anyway, 2-dimensional liquids crystallize really easily if you model the interatomic potential with the Leonard-Jones. And I actually tried myself to generate a model like this with Leonard-Jones and found that as soon as the thing assembled into a 2-dimensional assembly, it would crystallize. And if you want this thing to be fluid, you have to soften the potential. So what Ju Li did was actually soften the potential. Instead of 6/12, it's an 8/4. Do you guys even know what the Leonard-Jones potential is? I'm saying words you've never heard before. Raise your hand if you don't know what the Leonard-Jones potential is. Okay, the Leonard-Jones potential is a simple model of interatomic interactions. It has one term that goes like 1 over r to the 6 and one term that goes like 1 over r to the 12. It's shaped more like that, so that's u of r versus r. The energy of interaction between two particles at a distance r, and they have a sweet spot where the energy is lowest, a distance where they prefer to sit. Short range repulsion, long range attraction. We typically cut it off at a relatively short range distance, so it's easy to calculate. Okay, so in this particular case, we have a simple model developed by Julie and coworkers for a two-dimensional membrane that lives in a three-dimensional world. And it's fluid. Particles can move around. You can tear it apart. You can do all kinds of things with it. And what we said is we want to superimpose the XY model on the fluid membrane. Now we can have topological defects. And the XY spin we're going to attach to the membrane is like a flag on the toothpick on the tomato. Okay, the 4th of July is what, next week? When is the 4th of July? It's soon.
Yeah.
On the 4th of July, Americans like to have picnics to celebrate our independence. Okay, and we often like to have American flag decorations. And so if you're going to serve hors d'oeuvres to your guests, you might buy cherry tomatoes and stick a toothpick with an American flag. Okay, so the toothpick still represents the preferred layer normal direction, and the American flag now represents the tilt direction on my coarse grain particle. So one coarse grain particle now has 2 vector degrees of freedom, one vector representing the layer normal, one representing the tilt direction. It's fluid, it can move around, it can have topological defects in it. How is this different from the regular XY model? In the regular XY model, the spins can move around, but their center of masses are fixed in space, for instance, on a square lattice, or on the surface of a sphere, or wherever we put them. In this case, the particles can flow and move around. Okay, so it's a molecular type model. It's still going to be studied using molecular dynamics, but instead of thinking about an interatomic or intermolecular potential, we have coarse grain particles that are moving around in three-dimensional space that have X, Y, and Z translational degrees of freedom and 2 vector degrees of freedom, right, which represent the toothpick and the flag. The actual potential is here. I can explain it to anybody who wants to hear about it. The key issue is that this is not a crystal. This is a fluid of particles that can flow and move around, and it can contain topological defects. Can you see that? There's a +1 defect here and a -1 defect there. Now, even though we're representing a bilayer, this version of the model is 1 coarse grain particle thick. We don't have 2 sets of coarse grain particles separately representing what are called the inner and outer leaflets of the bilayer. We're just treating it as one, assuming that the tilt direction in the top leaflet and the bottom leaflet are the same, so we might as well just model it with 1 layer of coarse grain particles, each of which represents a big patch now of the whole bilayer. Okay, so the biggest number of particles we used to model the whole sphere was of order of magnitude 100,000. Okay, so there's all the details. So it's got an 8-4 type potential instead of 6-12, which keeps it fluid-like in a large temperature range. Okay, so what we did, we put the system, we actually tried just putting the particles randomly in space, and they will aggregate into vesicles, but that's a slow process. So instead of doing that, we just basically started with a sphere covered with these short-range particles, these short-range interacting particles, and then let them go, and they stay intact as a hollow sphere. We did not model the water. Okay, chemists have a very fancy name for that. They say the solvent is implicit, which is a way of saying we were too lazy to model the water. So we are using empty space to represent the water. It's the solvent in between. Okay, and what we saw, we started initially with all the tilt directions random on the sphere, and then let it relax. So we have dynamics for the motion of the particles and the reorientation of the 2 vector degrees of freedom. And what we saw was that initially a whole bunch of plus and minus defects nucleated over the whole sphere. Okay, and the total number of plus defects is 2 more than the number of minus defects. So the net topological charge is +2, as you might expect. Okay, and then they begin to parannihilate, and the vesicle begins to change shape. What we ended up with is something that isn't a perfect sphere. Okay, so simulation results. If we started with a rather small system, not too many particles, it was able to reach the ground state where only 2 plus defects were left. They are repelling from each other. They end up on opposite sides of the sphere. And the sphere indeed elongates. It's not quite as elongated as a cucumber, but it's definitely a prolate ellipsoid. Okay, so we were able to reach the ground state for a small system. But for a larger system, more defect pairs could get trapped. So the larger system I'm going to show you, we had about 100,000 particles. It starts as a perfect sphere. The spin orientations, like the tilt directions, are considered to be initially random, as if we just took the system through the phase transition from untilted to tilted, and the tilt directions are random initially. Okay, and then we quench it to low temperature and see what's going to happen. Okay, to visualize it, I'm going to show you a little movie. It has a black and white part and a color part. Okay, the black and white part is visualized as if we were looking through a single polarizer. That means, the reason we did that is because Linda Hirst's experimental techniques essentially only used one polarizer. When you look through at a +1 defect through cross polarizers, you see black whenever the orientation is parallel to one polarizer or the other polarizer, so you see 4 dark brushes. When you look through one polarizer, you only see 2 brushes. So where you see 2 brushes, that means a +1 or -1 defect. Okay, the color is showing how far the membrane is from its center of mass. So where it's red, it's sticking out like a pimple, right? You see red, it's protruding. And when you see blue, it's pushed in a little bit. So that just shows you distance from the center. And I think the next thing is the movie. Here we go. So, let me see if I can freeze it. No, it's not going to work. Just look at it. You see there's lots of defects initially, and as you watch, you can see parannihilation and parannihilation. These black dots mark the location of the defects, but it doesn't indicate which one is positive and negative, but you can see because they start to parannihilate. By the way, the student who did this simulation is named Jun Gang, G-E-N-G. Jun left physics and went to work at a hedge fund. Sad, he's actually quite good at physics. So at this point, you can see only a handful of defects are left. So at the end of the simulation, there are 10 defects. This is a +1 defect. You see that red region? That means near the +1 defect, the vesicle is starting to protrude, is starting to stick out and have tighter Gaussian curvature. I'll run that movie one more time. Okay, do you remember on the donut? The plus defects won't go in the negative Gaussian curvature region, and the negative defects won't go in the positive Gaussian curvature region. Once the vesicle has begun to change shape, if there's a +1 defect like on a mountain, on something sticking out, the minus defect has a repulsion from that region, and that inhibits parannihilation. So the coarsening process, the process by which defects parannihilate, is slowed down and perhaps even stopped entirely by the change of shape of the vesicle. Yes?
So it seems like as the system cools down, the localization of the defects are found in the protrusion region.
The plus ones go in the protruding regions. The minus defects flatten a little bit.
Okay.
Does that make sense?
Yeah.
Do you want to see it one more time?
I think I saw it.
It's already, you've seen it like 3 times, that's enough. Okay, so, yeah?
Glassiness is a symptom of indicator of glassiness emerging when final defects are there.
It's true. And like a glass, it's a metastable state. So my theory is if you took this vesicle and you pulled it with laser tweezers, you could stretch it out, it would reach the ground state, and when you let go, you wouldn't generate any new defects. So you could, by mechanical stress, overcome the energy barriers associated with defect parannihilation. There's only one problem. You might rip the vesicle apart. It depends how much stress it takes to deform it. I don't know. I'm a theorist. I've never tried laser tweezers. The only tweezers I have are the kind you take splinters out with. Right? So in this particular simulation, like I said, we had 100,000 particles, and it ran on a cluster. It wasn't a GPU code, it was an MPI code that ran on multiple processors. But even with that, even though they're coarse-grained particles, 100,000 particles was computationally demanding. We could probably go up an order of magnitude, but this seemed like enough. We only trapped 10 defects, which is like the 2 that are required by topology, plus 4 extra pairs. Okay, so we didn't actually make something that looked like a map of Australia. It wasn't as crumpled as the actual experiment, but the simulation demonstrated the idea that defect pair annihilation could be arrested by this shape evolution process. And the final shape isn't very disordered, but at least it's non-spherical. So our idea is that if we were able to do something that was maybe 1,000 times as large, and we trapped many, many defects, then we would see something that would look as crumpled as Linda Hirst's experiment. Yes?
So when we looked at the defects on the torus, you said that to keep the topological charge, you'd need 2, or 2 would be the minimum, but then you said because of the curvature you would have a minimum of 4 multiples of 4.
Okay. The
Analysis
Gauss-Pinay theorem depends on the number of handles. Remember how Mark taught us about handles?
Yeah.
Okay, on the torus you have 1 handle. The number of defects, total topological charge is 2 minus 2g, where g is the number of handles, or the genus of the surface.
Yeah.
So for a donut, for a torus, the total topological charge is 0.
Okay.
So you have to have plus minus pairs. What was peculiar about the picture I showed you is that when you have a skinny torus, the defects essentially make a grain boundary between clockwise and counterclockwise. And if you have one such boundary, you kind of have to have a second one.
Yeah.
So on the skinny torus, we had a minimum of plus minus plus minus. Topological charge is still 0, but you could have 0 or 4 or 8 or 12 or 16. You couldn't have 2 or 6 or 10 or 14. That's peculiar to the narrow torus. On the sphere, the genus is 0. 2 minus 2g is plus 2. So you have to have a minimum of 2 plus 1 defects. But you can have as many extra plus minus pairs as you like, and there's nothing special about having an even number of them. You can have any number of them. Okay, if we do it on a rigid sphere, like I put the XY model on a rigid sphere, if I anneal it slowly, they all annihilate until there's only 2 left. Those 2 repel and they go to opposite sides. The difference here is that number 1, the shape can change. Number 2, the particles are essentially represent a fluid membrane. Okay, so the whole thing can shear and flow and move around, and so it's a topologically. It's interesting because we have topological defects and shape change and fluidity. They're all different compared to the XY model on a rigid sphere. So the topology is the same, but the shape evolution is different. And so my argument here is that by inducing shape change in the membrane, you are able to get to a deeply metastable state. Now I asked Linda Hirst, if you let the vesicles sit around for minutes or hours or days, what happens to them? And she said they're completely stable, they don't change shape. Once they've been through the shape change, she puts them in the confocal microscope and looks at them, and she's like, it's not like you can wait a day and they will all go to the ground state. They are stuck in a deeply metastable, crumpled state. They don't ever reach the ground state.
Is this the area of the membranes conserved?
In this case, the number of particles is conserved. There's an issue in thinking about the symmetric A to C transition. Like if you have books on the shelf and you tilt them, it gets wider. So you would think that you would have more area, and it goes, something like this line and angle, you get extra area. But I think that alone is not necessarily sufficient to account for the crumpling. Especially when you consider, sometimes they leak anyway. So actually we had, Jim Gang developed an algorithm to keep the enclosed volume as a conserved quantity in the simulation. So we had a fictitious pressure on the inside of the vesicle that could conserve the volume. The fact is, if it's going to leak anyway, it's not necessarily conserved anyway, so we just turn it off, it doesn't matter. But for us, the key issue is that the number of particles stayed the same. Okay, so this work was published. If you actually want to see it, you can just look on my website at Kent State, but it was published with Linda Hirst in PNAS, I think just last year. Okay, now let me ask another question. What if the lipid, instead of having an XY type symmetry like a tilt, what if it were a nematic? So it's still like an XY model, but instead of having an arrow on the vector, you basically have a vector with no arrows, or if you like 2 arrows, right? The 2 sides are the same. So for instance, you could imagine a lipid shaped like the letter T, okay? So if you have the lipids with their tails along the layer normal, but the heads are free to rotate, and two lipids that are next to each other want their heads to align this way or that way. Now, I know there are a lot of people studying T-shaped lipids, but I haven't seen an experiment yet, and I haven't gotten Linda to do one for me, but maybe she will in the future. But you could imagine in that particular case, I bet Mark might know. Mark, have you done a lipid that's really nematic? So this is now an imaginary lipid. Not T-shaped. So we know from work of Nelson and many other people that in that case you would expect on a sphere, if you had a sphere that had a nematic character, it has to have 4 defects of charge plus 1/2 each at the minimum, and it could have extra plus minus pairs. Okay, so the question is, what would happen if you had a nematic that was flexible, a nematic membrane in a sphere shape, and it was flexible? Park, Lubensky, and McIntosh, and Fred McIntosh, asked this problem way back in 1992, and they said, well, again, each of those little defects would cause the curvature to change. So you would get something that looks a little bit like a spaceship, right? Except it's not really a spaceship. It's not circularly symmetric, right? It's like a tetrahedron that's a stuffed animal because it's got like curved corners. That's their idea. Okay, so if you had a vesicle and it had 4 defects on it, it would make that shape. And so we thought we would try using our coarse grain model and see what we could get. So we took, here's our cherry tomato, and there's a toothpick, and now at the top, instead of a flag, we have a bar. Bar has 2 equivalent ends, they're equal to each other. So this is, again, a coarse grain model of a lipid. It has that particular symmetry. And there was a parameter in the model that controlled the strength of the coupling between the bending and the curvature and the defect, and that was an adjustable parameter. So we looked at how the thing, different shapes it made. So the first thing is, if we started the system as a sphere, and it had, the 4 defects, what shape? It's going to deform a little bit because those defects, are coupled to curvature. So those black spots represent the location where the defects are in our coarse grain model. And the first thing is looking at it and saying, you know what? It doesn't look anything like that. It doesn't look like a tetrahedron with curved corners. It looks more like a potato, right? It's a little bit stretched out, and the defects can either be in a rectangle or they can be twisted like this. In this particular picture, I think they're twisted a bit, so they're not in a rectangle, they're kind of rotated like that. So immediately, it disagrees with the theory that was in the literature. If we turn up the coupling even more, the defects actually start to open up as holes, okay? Because the coarse grain particles are so weakly bound because the orientations are so violently disturbed that they start opening holes. And if we run the system forward a little bit further, the 2 defects at each end more or less merge to make a hole, and we end up with a tube. So we have a morphology transition from a vesicle that's round and has 4 special defects. And if we increase the coupling, as if, for instance, we were changing the temperature, has a phase transition to a tube, which is kind of interesting. Now, in this particular case, we didn't make the system large enough to have extra plus minus pairs. So the system is in the ground state, right? Just the minimum number of defects at each time. But it's interesting that it shows this morphology transition. Now, just for something a little bit fun. Do you guys know about the little magnetic spheres that were sold as toys? They were sometimes called Bucky, what were they called? Bucky spheres? Did people call them actually Bucky balls?
I think so.
It was a brand name. They're just little spherical magnets. They are no longer sold in the United States. Did you know that? Are they sold here? Here's why they are dangerous. If children swallow 2 of them, they can actually cause death. 1 is safe, 2 is dangerous. You know why? Why are they dangerous? What can go wrong if you swallow 2 small magnets? Right, they trap 2 parts of your intestine together, and then they rub, and then actually cut a hole in your digestive tract and kill you. Right, you die of sepsis.
But if you get the 2 at the same time, they stick together from the beginning.
Then you should be fine. Okay. If they stick together from the beginning, you should be fine. Actually, I have to tell you. No, and the reason they're dangerous also is when you're playing with them, it's easy to drop one and then they're on the floor and you forget it's there, and then, you know, like 2 years later you have a kid and your kid finds it and they eat it, right? So you have to be careful with these things. So if you own buckyballs, and I actually have sets of thousands of them, right? If you own buckyballs, just keep them safe, don't let them fall on the floor, and keep them away from children. I'd have to tell you a story that's amusing. It happened to a child I know. He was at a party where there was a gift for each child at the party. It was a little blinking LED light and a magnet. And you could stick it on your shirt. You put the light on the outside, you put the magnet on the inside. No pins, right? And you have a blinking light on your shirt. Isn't it great at the party? The lights are down and everybody's lights are blinking and it's a nice party environment. Well, my son's friend, his name is Sam. Sam said, hey, I think that would look really nice on my nose. So he puts the light here, he puts the magnet on the inside of his nose, and he's got a blinking nose ring. How cool is that? You know what's better than one blinking nose ring? 2 blinking nose rings. So he asked our son, hey, can I have your light? Our son's like, sure, here. So he has one here, he puts the other one here. He puts, one magnet's on this side, he puts the other magnet on this side. The 2 magnets pop together on the inside of his nose. So high on his septum, he can't reach them. He had to go to the emergency room. Don't let your children put magnets in their nose. And this child was 13 years old when this happened. We're not talking about a toddler. Anyway, this is all I'm going to say. I love to play with magnet beads. I want to show you this little movie. I made this little movie. Each of these hexagons is an assembly of magnet beads with the dipoles going around in a circle. Okay, so there's dipole chains in each ring, and they have an interaction. And this creates a 6-fold symmetry in their interaction. The bead in the middle has an unmatched dipole moment and is actually resting slightly below the rest of the hexagon and represents a pivot point. So these things are just sitting on a table, and I can put them close enough that they interact with respect to each other's magnetic field, and they represent coupled spinners. Okay, and I have one of them spinning there, and as it's slowing down, it's transferring its kinetic energy to the others through the magnetic interaction. So because these things are 6-fold symmetric, they have a 6-fold symmetry, and this is to introduce the idea of n-atic order. Okay, n-atic order. Also, you can learn a lot of physics from playing with toys. Okay, so the question is, if you had a vesicle made out of a lipid that had n-fold symmetry, not just like an X-ray model or like a Nematic, but you could have all different things, then in that same paper I mentioned before, in principle you should be able to get vesicles of different shapes. So this is a good excuse to talk about n-atic order in 2 dimensions. Okay, so the n equals 1, can you guys see the little arrows there? That's the XY model. 1-atic order is the XY model, it's polar. Okay, with n equals 2, it's a nematic. The arrow has 2 heads, okay, and that's nematic order. This is triadic order. You have little triangular objects, and you can have n equals 4, 5, 6, there's no limit. Okay, so 6-fold is like what I showed you. Tetratic, pentatic, whoops. So n equals 1 is our familiar polar order, and we have defects of +1 and -1. Okay, n equals 2 is the nematic, which has defects of +1/2 and -1/2. I hope by now those are starting to feel like old friends. We love those topological defects, right? What about n-atic? So the point is, if you have n-atic order, your interaction, okay, so for n equals 1, it's cosine, like the dot product, right? For n equals 2, it's cosine 2 theta. For n-atic, it's cosine n theta. Defects +1 and -1 there, +1/2, -1/2. For n-atic, it's defects of 1/n and -1/n. What do they look like? Well, let's look at n equals 4. Here is a defect in a, what is it called, tetratic with n equals 4. And you can see if you take your pen and point it, say, along the north direction here and go around, it only rotates by pi/4 degrees, right? Is that right? It rotates by 90 degrees around the defect 4. So that's a topological charge of +1/4. If you put that on a sphere, and you have to have a total topological charge of +2, you need 8 of them, right? Because they're only carrying 1/4 charge each. All right. How about looking at those defects? So here's our n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. It gets hard to see. I don't even see the defect there. It's like invisible to me, but it's there. It only rotates by, what is it, pi over 6 going around. So these are a different class of topological defects, right? But it denotes a material of different symmetries, can have different types of topological defects. Okay, so in this beautiful work by Park, Lubensky, and McIntosh, they considered what happens to all those different shapes. I already showed you the n equals 1. This is kind of like the cucumber. Their solution looked more like a watermelon than a cucumber, but it's still a prolate ellipsoid. Their n equals 2 looked like a stuffed animal tetrahedron. Here are some of their other pictures. So the n equals 3, 6 defects on the sphere. N equals 4, 8 defects. N equals 6. They didn't do n equals 5. They skipped 5. I don't know why. I wish they'd done 5. But anyway, 12 defects at charge 1/6 each. Okay, and so the question is, could we take our model and make it do all of those things? Well, we tried. So we took that same model developed by Julie and added the extra terms to represent n-atic order. Okay, and instead of just the special direction, which would be appropriate for polar order, we put a bar on that would have the appropriate symmetry. So you can imagine sticking a snowflake on top. When would you serve a cherry tomato with a toothpick and a snowflake on top? Would that be a snow party? I don't know. Oh, you could have, if you were having a party with the theme of the movie Frozen, you could do that maybe with cupcakes for your children. They might like that better than cherry tomatoes. Okay, so the n equals 1 I already showed you. The polar thing can make all those things. N equals 2 I already showed you. Here are some of the other things. So here is n equals 3 and n equals 4. Here is, from our coarse-grained model, what the disclination actually looks like. And you can find the rotation in here. And here's the n equals 4 case. And you can count the defects, and yes, we got the right number. However, because we had the problem that if we ramped up the coupling between the defects and curvature, the whole thing could blow apart or start having particles in the core of the defects actually fly out and have the whole thing break up. We couldn't get big deformations, but we got the right symmetries, which is kind of interesting. Yes?
Why am I saying that the simulation doesn't agree with the theory?
It doesn't agree with the theory, partly because the coupling between the defects and the curvature is not strong enough to deviate too much from the spherical shape. So that's, I think, why they agree in the sense that they both obey the Gauss-Bonnet theorem, they both have the right number of defects, but we don't have much shape deformation. So we weren't really successful in testing the theory, but it doesn't look even close at this point. Here's n equals 5, and of course, Lubensky and McIntosh did not do the n equals 5 case, and here's the n equals 6 case. But at least we can demonstrate that the topological defects have the right sign and that there's the right number of them, but that pretty much had to be true. Okay, it's almost 12, and we have one more lecture, so I'm just going to tease you a little bit with what we're going to talk about tomorrow. A nematic, I'm actually not lecturing tomorrow, Friday. We're going to talk about defects in stretchy polymers that have a nematic character. And here you can see a nice Schlieren texture, a defect texture in this nematic elastomer. This is a computer simulation performed by Bedel Mbanga, who is a student from Cameroon, currently a postdoc at Tufts University. And as he's stretching the material, the defects are disappearing. Ooh, so we're going to study that. So in this case, the defects are mobile, but the material is not fluid, it's elastic. But we can still have changes in topological defects. And we can have a sample that has a +1 defect in it. These simulations were done by Vianney Jimenez Pinto from Venezuela. And we can actually, plus defects induce positive curvature, minus defects induce negative curvature, which looks like a saddle. And this simulation was done by Andrew Konya. These are finite element simulations. A +1 defect, as it's heated, can form something that looks like a Mexican hat. Okay, and then after it's heated further, relaxes into a cone. So we're going to talk about how patterning topological defects in a polymer film can produce auto origami, a material that can spontaneously and autonomously shape itself into complex shapes because of the presence of topological defects. That's what we'll do on Friday. Anyway, I'm happy to answer your questions now about anything I talked about today. You know, I kind of have to train my classes to applaud at the end of every lecture. I like that a lot. You know, Dave Waits has a tradition. He has a wonderful class he teaches at Harvard about learning physics and chemistry and material science from food and cooking. And they have a rule that whenever you show an equation on the board, you have to applaud. Isn't that right? And there was something else about desserts. What do you have to do when you see a dessert? Do you remember?
No, but I think they're limited to one question, one equation.
One equation, like per week or per day?
Per class.
Per class, okay. Did I show you? I showed you some pretty icky looking equations, but I didn't make you look at them. Right? If anybody here is interested in learning how to do molecular simulation, you don't have to write it from scratch. There's many molecular simulation codes out there. One of my students is using Bromax, which is a molecular simulation software. But it's a good idea to learn how to write them. It gives you a lot of power in terms of computer simulation methods. All the simulations I showed you today, everything was homemade. No commercial software was used. So, yes?
Bilayers, there can be two different plus one defects.
There can.
Yeah, because one will show like that.
One can be in the top and one can be on the bottom.
No, yes, one can be like, if this is all happening, this is the bottom, this is the top, yeah, it can be like this, or like this. It would show together the arrows or away.
Well, it's funny that you brought that up. So the student, Jim Gang, did take Julie's model and mess with it further and make two-dimensional versions of it. And I think I might have some pictures. So that's the cartoon. Let's see. So this is the showing bilayer formation with the version of the model where the lollipops like to stick together like that. But this one's not tilted. This is just without the tilt. And starting from just putting the particles at random in the box and letting them relax, they spontaneously, I don't know if you can see, but there's like, you see that little blue stripe, that means that it's formed a bilayer and it's spontaneously curved. Even though there's nothing in this model that favors curvature, it's spontaneously curved, and so it started forming vesicles. You can actually make a lamellar phase, and this is another kind of topological defect. This looks like a smectic, but it's made out of bilayers. Okay, and at this particular density, he quenched it fast enough that instead of making like regular layers all the same, that's an edge dislocation. Probably not physical because it has an end that's not rolled over, but yeah, so it is interesting to consider the inner leaflet and the outer leaflet separately. And certainly within biological cells, the chemistry of the inner leaflet and the outer leaflet are not identical, or you can have proteins that poke through all kinds of, I'm sure there's people here that know the biochemistry far more than I do. But so from your point of view, the top one can be pointed this way, and the bottom one can be pointed that way.
Also, the top one can be pointed in different ways. If you have symmetric C, it is tilted.
It can be this way,
Yes,
or it can be tilted.
like this, or this, and also at the top. So it should make it different results.
If you think about an XY model on a sphere, you pretty much have to have the arrows pointing in on one side and out on the other side, or pointing around on both sides. I would guess for the lipid, you're more likely to have the tilt direction pointing around rather than directly in. Does that make sense to you? And then it would mirror on the bottom leaflet to the top leaflet. Jin Gang did not run the model with tilt in the bilayer version though, so I don't have any data to answer your question. I'm wondering whether Linda Hirst, with her confocal microscopy, could separately image the upper leaflet and the lower leaflet. Yvonne, could it be done with cars?
Unless you do some specific labeling, that could be hard just because of resolution, have to be a nanometer or so.
It's
But
hard.
if you do separate labeling with different dyes or something like that, then that could be possible.
There are certainly a lot of biochemists and lipids specialists who are interested in what's happening differently in the inner leaflet and the outer leaflet and how frequently lipids are exchanged between layers. Since I have like 2 minutes left, I'm gonna ask you one more puzzle. In smectic liquid crystals, they're layered, right? If you look at diffusion in the smectic, a molecule in a layer can diffuse rapidly in the layer. It's liquid-like, right? It diffuses around in the layer. But it can also have diffusion between layers, diffusion up and down. What role could topological defects play in determining the ratio between layer diffusion and in-layer diffusion?
More defects, more between the
Which kind of defect?
plus one.
A plus one? I need something that connects the layers, a screw. Okay. If you're in a parking garage and you're drunk, don't ever do that. If you're driving around a parking garage and you're drunk, or maybe you're just lost and you're wandering around the parking garage in your car. Or you could do it walking, it would take longer. If you accidentally circle a screw dislocation, you end up 1 floor above or 1 floor below, right? Likewise, if you have screw dislocations in a smectic and you have a particle that's diffusing in layer, if it accidentally diffuses around a screw, it will go up or it will go down. So many years ago, I was at a liquid crystal conference and I met one of the most brilliant liquid crystal simulators in the world, Claudio Zanoni. And we were talking about this business of, there were experiments on diffusion in smectics and the ratio of out-of-plane diffusion versus in-plane diffusion. And he'd done a simulation of a smectic with thousands and thousands of molecules in layers, and he never saw a molecule jump out of one layer and join a different layer. So since he never saw it over the nanoseconds of his simulation, he could say, well, I can put a limit on what the diffusion ratio could be because I never saw it. And I said, but what about the screw dislocations? And he said, well, what difference do those make? And I said, well, they're omnipresent. You cannot get rid of the screw dislocations in the experiment. And so the experiment that measured in-plane versus out-of-plane diffusion had screw dislocations. And the simulation that he did was completely clean with no such defects. Okay? So here's what I learned from hanging around with metallurgists. Transport depends on microstructure. Microstructure is defects. Okay? So if you don't understand the defects in your material, you don't understand its properties. Okay? So the joke for people who work in real estate, like buying and selling houses and commercial buildings, they say the 3 most important features of any property to determine its price are location, location, and location. Did you ever hear that joke? It's a joke. The 3 most important things about any material are microstructure, microstructure, and microstructure. Rheology, transport, thermal conductivity, everything depends on the presence of defects. Defects are valuable. All right, it's 12. I'm stopping. We have one more presentation this morning. Where's Christian? Is he here?